Hello. So welcome back. This is AMAT 104 lecture recording, week 1.2. So here, week 1.2 implies the second lecture of the first week. Okay, so before we begin anything, a quick reminder that make sure you join Pearson. And gain access to this class on MyMathLab. Okay, so please make sure you do this because currently we do not have any homework, but when we do, all your homework assignments will be on Pearson and all your grades, all your quizzes will also be on there too. So if you do not have the access to the Pearson, you won't be able to access any homework assignments, quizzes, exams, or anything like that. So please do so before it's too late. If you have any trouble doing so, please shoot me an email and hopefully we'll figure out how to do so. So last class, we talked about the sequence. Let's recap a little bit. So last class, we defined the sequence. So the definition of the sequence is this is an infinite and ordered list of numbers. And we looked at a few examples of sequences, and we also looked at something that's a little more exotic too. So, and the notation that we looked at was when we say a sub 1, a sub 2, a sub 3, dot, 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 let's say a sub n, a sub n plus 1, and this is where this implies the infinite, indicates the infinite numbers. So here, this a sub 1 implies the first term of the sequence, and a sub 2 is the second term, and so on, and a sub n would imply, well, will denote the nth term. And here the subscripts 1, 2, 3, 4, 5, n plus 1, and so on. It's just a placeholder just to indicate where this number locates within a sequence. So I think that's where we ended last time. So let's look at a few examples. So okay, so the sequence described by a nice formula. Let's say a sub n equals to 2 to the power of n plus 1. Here, if you want to find the first term of the sequence, you would simply substitute 1 for every n you see. So the first term of the sequence will be defined as 2 to the power of 1 plus 1. So this will be 2 plus 1 equals 3. So here, the first term of the sequence is 3. Then what about the second term? Let's say here, a sub 2. So as we did here, we would substitute 2 for wherever you see n here. So 2 to the power of 2 plus 1 will be, so 2 to the power of 2 is 2 times 2, which is 4 plus 1 equals 5. And we could do the third term of the sequence as 2 to the power of 3 plus 1, which is 8 plus 1 equals 9, and so on. So this is a very nice formula, and the sequence, you can find any term of the sequence simply by plugging in numbers. Then that way, you can simply find the 100th term, so which is denoted by a sub 100. You can simply do 2 to the power of 100 plus 1. So in this case, this is a very large number. So I am not going to calculate the 2 to the power of 100, but this is just the principle of how this works. So formulas like this, formulas that are given like this, it's actually called the explicit formula. So explicit formula is simply a formula like this which involves n, where you can simply plug in n for the location of the term and the sequence and simply find out something like this. So let's look at another example, which is a little more complicated. Well, not really complicated, but a little different. So I'm sure some of you have already heard of this thing called Fibonacci sequence. So Fibonacci sequence is actually given as 1, 1, 2, 3, 5, 8, 13, 21, and so on. So how the numbers are determined is that given the first two terms as 1 and 1, the third term of the sequence is determined by adding 1 plus 1. So adding the first two terms of the sequence. And the fourth term is actually given by 1 plus 2. Fifth term is given by 2 plus 3, and so on and so forth. So in this case, each term is determined by the previous terms. This is not an explicit form. This cannot be, I mean, well, there is an explicit formula for the Fibonacci sequence, but in this case, it's very complicated and it's very exotic, and it's not very useful, let's say that. So in terms of sequences, for sequences like this that are determined, where the terms are determined by the previous terms in the sequence, we actually call this a recursive formula. And this is actually determined by, let's say, f for Fibonacci so we can say that f3 is determined by f1 plus f2, just like how we found the 2. And before that, we know that f1 is 1 and f2 is 1 as well. And we also know that f4 is now determined as f2 plus f3, and so on. So this is called the recursive formula, and we define the Fibonacci sequence, let's say f sub n, as f sub n minus 1 plus f sub n minus 2. So this may look a little complicated, but if you plug in each number here, so for example, if you, let's say, plug in 5 in here, 5 minus 1 is 4, and 5 minus 2 is 3. So we know that now f sub 5, which this number is, so 5, is determined by the fourth term and the third term. So that's 3 plus 2, and we can see that this works all the time. And as I said before, this is a recursive formula. So recursive formula is not always possible, and as well as the explicit formula. Not all sequences are defined by the explicit formula, as well as not all sequences are determined by the recursive formula. Some have both, some only have one, but for different situations, different sequences, one may be easier than another. Now let's define something else. So we're going to go through more examples of the explicit formula and recursive formula later today in this recording. But before I do that, I just want to define just one small thing. So let's say population sequence. A population sequence so this is the keyword, describes the size of a population as it changes over time. And it's measured in discrete time intervals. So here discrete means countable. It's the same meaning. Opposite word will be continuous, so it's opposite to continuous. So here the notation goes, a population sequence starts with an initial sequence. So initial sequence is denoted as P sub 0, as P represents the population, and the 0 means initial, so nothing has happened yet. That's what you're starting with. And after time goes by, so discrete measure of time, so normally after, it could be years, hours, or even seconds. So these are all discrete time intervals because we can count number of years, number of hours, and number of seconds that's elapsed. Then we have a changes in population. The change could be increasing or decreasing, or it could stay unchanged. So, so there is a change. In the population. And this could either increase or decrease or just stay unchanged, just all the way through. And we call this a transition. So the notation is really similar to the regular sequence that we talked about before, but in this case, the only difference is that we use P instead of A, and we start from 0 instead of 1. So P sub 0 implies the initial, well, denotes the initial population, and P sub 1 is the population after one generation. And P sub 2 is population after 2 generations. P sub 3, oops, so P sub 3, and so on. And we have population after nth generation, and it continues because it's a sequence. So this is a very important notation because it's very useful in different growth models or decay models that we're going to go over in the future lecture videos. And it's very useful because it's very applicable to real life situations where you can predict regarding whatever it is, you can predict knowing the model. You can predict the future population. So I use the word population, but it could be anything. It could be the number of cases of COVID. That's just one thing. But this can be used to determine the simple modeling of any increasing, decreasing, or even steady population or data like that. So so that's the end of 9.1. And before we go into 9.2, I actually want to go over a few problems. So a few examples where you might encounter trying to do your homework. So this is an example from a textbook. This is actually from a textbook, and all your homework assignments that will be on Pearson are actually from the textbook. If you get the access to Pearson, you will have an access to the ebook, like an electronic copy of the textbook, and you can actually see all these problems there. So let's start with the first one. So consider our sequence defined by the following formula. So you're given a sub n equals to 2n to the power of 2 plus 1. So before we do anything, is this what kind of formula is this? Is this explicit or recursive? So here you can see that this formula, even though it looks a little complicated, does not depend on any of the previous terms in the sequence. In order to find n term of the sequence, you just have to replace this n with a certain number. So in this case, this is the explicit formula. This is not the recursive formula. So with knowing that this is an explicit formula, how do you find the a sub 1? In other words, how do you find the first term of the sequence? It's simple. So it's already given that you have to substitute 1 for every n you see. So you'll simply do 2 and you substitute 1 in the place of 1 and make sure you put the bracket there or parentheses there. 2 plus 1. So by now, I assume that you understand the order of operation. So here, 2 and this 1 to the power of 2 is multiplication. There is a hidden multiplication there. And plus 1 is obviously addition. So when it comes to multiplication and addition, you always do the multiplication first. So before we do that, we know that 1 to the power of 2 or 1 to the any power is this 1. So it's 2 multiplied by 1 plus 1. So that is what? 2 by 1 is 2 plus 1. That 1 comes from here. And you have 3. So we know that a sub 1, or in other words, the first term of the sequence that's defined by this explicit formula is 3. That was simple, right? So similarly, you would simply plug in 2 to find 2 to the power of 2 plus 1. And you do 2 multiplied by, what's 2 to the power of 2? So 2 to the power of 2 is 4 plus 1. And since you do the multiplication first, you will end up with 8 plus 1, which is 9. So that was simple. But now you're given something ridiculous. Let's say a to the 400. It's a big number. If you, but you simply do the same way. So given this formula, you're simply plugging in the number 400 for every n you see. So here you would have 2, 400 to the power of 2 plus 1. Obviously, that's a big number, and usually Pearson requires a very specific answer. So here, this is where you would use your calculator. If you put this into a calculator correctly, you would end up with 320,001. So from going here to here, use calculator. Okay, so that was simple. That's something that we have already seen before. But what if you're given something that's a little different? Let's say the question asks, if a sub n equals to 19, then what is n? So up to this point, we were given a formula and we had to plug in a certain number to n to find the corresponding term of the sequence. But in this case, you're already given the term of the sequence and you are to find what n is, or in other words, what nth term, or when does this number 19 come along in this sequence. So the way you approach this is the other way around, but it's also simple. So you're already given that a sub n equals to 19. So bring this formula down here. So given a sub n equals to 2n to the power of 2 plus 1, we know that a sub n as a whole is given as 19. And now what? Now all you have to do is solve for n. I'm sure you've done this several times back in high school or in other math classes. So in order to isolate the n on one side and put everything else on the other side, what's the first step? So you would subtract 1 on each side to get 2n squared, and you'll get 18. And from here, to isolate the n by itself, you would divide both sides by 2. And then you would have n squared is because 2 cancels by itself, and 2 and 18 cancels to be 9. You get 9 there. So when n squared equals to 9, it's easy to see that n is 3 because 3 squared is 9. Does that make sense to everyone? Okay, so that's a sample example of what the type of problems that you'll see in homework problems. Let's do some more examples of maybe a little different things, just so you get more familiarity before you actually tackle different problems yourselves. So, different example. So let's say now you're given a formula that's defined as 6n over n plus 5. It's a little more complicated. Now it's in a fraction form, but it really isn't that hard at all. So simply, if you want to find a sub 1, which is the first term of the sequence, as we've done several times by now, you simply plug in 1 here. So here dot represents the multiplication, and you plug in 1 for every n you see. So what's 6 times 1? So anything times 1 is the number itself, and 1 plus 5 is also 6. And now you can simply see that 6's can cancel out, and you have 1. So in this case, with this explicit formula, you have found that the first term of the sequence is 1. Then what about the 6th term of the sequence? So in order to find the 6th term, we do the same way. So you plug in 6 for every n you see. So 6 multiplied by 6 divided by 6 plus 5. So 6 times 6 is 36, and 6 plus 5 is 11. So can you simplify more from here? 36 over 11. The answer is no. So in this case, you would just leave it as that. Most of the time, unless the problem asks you to express in decimal form, fraction is always more accurate. So unless you're asked to do so, please leave it in an exact form as fraction, because if you convert this into decimal, it's going to end up being an approximate number, and the Pearson will ding you for that. So make sure you do that. So leave the answer in fraction. I know a lot of the times if you simply plug this number into calculator, it will output decimal form, but do not do that. So something similar to the previous problem, what if you're given a problem saying that, what if a sub n is given as 9 over 2? Then what is n? So it's simply the same problem. So you are approaching this problem as we did up here with 19. So what did we do there? So we brought the formula, the given explicit formula down here, and we simply let a sub n equals to 6n over n plus 5 is what we were given. And we know that the a sub n as a whole is given as 9 over 2. So there are many different ways to go about solving for n in this case. Some of you like to cross multiply like this, or you can simply multiply by 2 on this side, multiply by n plus 5 on this side. It's all the same thing. They're all the same principle, just worded it differently. So let's do cross multiplying. So in this case, you can multiply 6n by 2, and you can also multiply 9 by n plus 5. Then what are you given? So you're given 2 multiplied by 6n, and that is the same as 9 multiplied by n plus 5. So make sure you put the parentheses here, because otherwise you're going to get a wrong number. So on the left-hand side, 6 times 2 is 12n. On the right-hand side, you would have to distribute the 9 on each number. So 9 times n is 9n plus 9 times 5 is 45. Then what you would do is you would have to put all n on one side. So what I'm doing here is subtracting 9n on from each side. So the right-hand side, you'll end up with 3n. And the, sorry, left-hand side, you'll end up with 3n. And the right-hand side, you'll end up with 45, because 9n's cancel each other. So we're almost there. So we have 3n that's given as 45, and simply by dividing 3 on each side, you can find that the right-hand side is 15, hence we have n is 15, and that is what you needed to find. Let's now go over a problem that involves a recursive formula. So let's consider a sequence that's now determined with, by a recursive formula instead of explicit formula as 3a sub n minus 1 plus a sub n minus 2. So why is this recursive formula? What makes this formula recursive but not explicit? So this is a recursive formula because each term of the sequence is determined by the previous term. In this case, to find the a sub n, you need to know the a sub n minus 1 and the a sub n minus 2 just to find the term of the a sub n. So when you're given recursive formula, you're normally given, you're almost always given the first terms of the sequence. So in this case, a sub 1 is given as 3, and a sub 2 is given as 3 as well. So the reason why you're given the first few terms in the sequence is because without these, without the first term and the second term, you won't be able to find a third term. Also, similarly, without this, you wouldn't even know how to find the first term because there is no such thing as previous term to the first term. So now knowing that a sub 1 is 3, a sub 2 is 3, given this recursive formula, how do you find the a sub 3? So in other words, the next term in the sequence. So a sub 3, if you plug in 3 for every n you see, you'll end up with a sub 3 minus 1 plus a sub 3 minus 2. And that is simply 3 sub 2 plus a sub 1. Does that make sense? So here the numbers are subscripts. Do not write it big next to a's. So now you have this new formula, and we know the a sub 2 and a sub 1. It's given from the problem. So in order to find the a sub 3, you're simply doing 3 multiplied by 3, which is a sub 2 here. And you would add the a sub 1, which is given as 3. So 3 times 3 is 9, plus 3 is now you have 12. What about a sub 4? So we now know that this recursive formula consists of 2 previous terms. So a sub 4 is determined by 3 multiplied by a sub 3, which is the previous term, plus the a sub 2. Do you all see why this is the case? And we're given a sub 2 from the problem, and we also know that a sub 3 is defined as 12 because we just calculated it. Then that way we can simply plug it in. So 3 multiplied by 12 plus 3. And that is going to be 39 because this is 36 plus 3, and that's 39. So in this case, I'm sure these are easy enough calculations for you, but it's always a good practice to double check with the calculator to make sure that you are on track, because what happens is, because each term is determined by the previous terms, if you calculated the, let's say, ace of 3 wrong, so if this number was wrong, this will also be wrong consequently. So make sure that you check every little step as you go along. Otherwise, you're going to end up with a bunch of wrong numbers, and it's going to be difficult to track down where you messed up. Let's just do one more. So ace of 5. So we're now used to this. So ace of 5 is determined by 3 multiplied by ace of 4 plus ace of 3. So now that's 3 multiplied by 39 plus ace of 3 is 12. I think 3 times 39 is 117. I think that's right. So plus 12 should be 129. And you can use these numbers to find the ace of 6 and ace of 7 and so on. Does that make sense? So the next example that we're going to look at is a little different. So up until now, we're all given some sort of formula. We are all given either explicit formula or recursive formula. But what if you are not given anything, but instead you're given a random sequence and you are to find a formula like that? So this could be a little challenging for a lot of you. And I had a lot of students having problem with this specific problem, but let's start with this. So you're given a sequence that starts with 125, 216, 343, 512, 729, and so on. So these look like a bunch of random numbers, and you are to find the next term. So this will be the first term, second term, third, fourth, fifth. So what's the sixth term? How do you find the sixth term? So in problems like this, it would normally take a longer time than the other problems, because you do not really have a specific guideline how to go about this. You just have to fiddle around with the numbers and see the difference between the two, and you are to find patterns. So in this case, 125 is actually 5 cubed. So it's 5 times 5 times 5. 216 is 6 cubed. 343, 7 cubed, 8 cubed, and 9 cubed. Then what would be the next term? So logically, you can see the patterns here. It goes from 5 to the power of 3, 6 to the power of 3, 7 to the power of 3, and so on. Then the next term would logically be 10 to the power of 3. So what's the 10 to the power of 3? So it's simply 1,000. So now that you know the pattern, it's easy to see how these numbers came along. But sometimes you'll encounter problems like this without any guidelines like this, and you are to find out the terms or even find the explicit formula. This could take up longer time for you, but this will be a good practice for you to see many different types of numbers. So a related problem to this, let's say if the sequence is denoted by a sub 1, a sub 2, dot, 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 how do you determine the a sub n? In other words, how do you find the explicit formula? So let's go step by step. We know that a sub 1 is 125, or we now know that it's 5 to the power of 3. A sub 2 is 216, which is 6 to the power of 3. And a sub 3 is 7 to the power of 3, and so on and so forth. So in this case, you can see that the power of 3 stays the same, but just the numbers in the bottom. So we know that you have, if you want to find some explicit formula, it has to be in some form of n. It has to involve some number n where you can simply plug in to find these numbers. So in this case, for example, for a sub 1, for any explicit formula that you have, if you plug in the number 1, it has to output 5 to the 3. If you plug in number 2, it has to be 6 to the power 3. So this usually takes longer time for most students, but here is how you go about it. So you know that a sub 1 is 5 to the 3, and that way you can simply see that you're only increasing. So and for a sub 2, it's 6 to the power 3, and it's only going up by 1 in the base numbers. So simply how you approach this problem is you let this a sub n become some number, and some number in there, in this case would be 4 plus n to the power 3. So that way, if you plug in 1, it becomes 5. If you plug in 2, it becomes 6. If you plug in 3, it becomes 7, and so on and so forth. And this actually is the explicit formula. I know for most of you, this probably did not make logical sense, but the problem itself is not, it's more to get you used to many different sequences, and it really doesn't have any logical steps to it. It's more of an intuitive decision, and the more you see it, it's going to be more evidence for you. So let's look at a notation. So here we defined it as a sub 1, a sub 2, and so on. But in population sequence, so let's say the population sequence you are normally given from the initial population P1, P2, and so on. So if the sequence was the population sequence, then it starts from 0 instead of 1, and you are to find the explicit formula for the P sub 1, a P sub n. How would you do it? So it's the same thing. So you have p sub 0 that's given as 5 cubed, p sub 1 is 6 cubed, p sub 2 is 7 cubed, and I'm sure a lot of you have already noticed that you plug in 0 to get 5, 1 to get 6, 2 to get 7, and so on. So in this case, you actually end up with p sub n equals to 5 plus n to the cube. So that way, if you plug in 0, you get 5 to the power 3. If you plug in 1, you get 6 to the power 3. If you plug in 2, 7, and so on and so forth. Did that make sense? So let's look at maybe one more example before we wrap up this lecture. Let's consider the following sequence. And it is given as 3 over 9, 6 to 10, 9 over 11, 1, 15 over 13. Do you guys see any patterns in this example, in this sequence? So some of you have already seen this, but up here, it's actually going 3, 6, 9. It's a little weird, but we have 15. And we can kind of deduce that the numerator is going up by power of 3. No, sorry, going up a multiple of 3. So in this case, you can actually simply change this number 1 to 12 over 12. And that way we have 3, 6, 9, 12, and 15. So we can see that the numerator is going up by multiples of 3. What about the denominator? So we start from 9, 10, 11, 12, and 13. So it's only going up by 1. So denominator is going up by 1 each time. So what's the next term? So let's say this first, second, third, fourth, and fifth. Then what's the 7th term? So the next term will be, logically, because we're going up by multiple of 3, so after 15, if you add 3 in there, it's going to be 18. And in the denominator, because we're going up by 1, it's going to be 14. And the 8th term, we're going up by 3 in the top, so it'll be 21, and going up by 1, so it's 15. So how do you find the explicit formula? So what if you're trying to find the explicit formula A sub n? So in the numerator, we can see that it's going up by 3. So you're simply putting 3n. So that way, if you plug in 1 for the n, it becomes 3. If you plug in 2, it becomes 6, 9, 12, 15. But in the denominator, it starts from 9. It doesn't start from 1. So how do you do that? So actually, we're going to use the same tactic we used before. So up here, in order to make the 5 in the first term, we added the 4 there, and we're going to do exactly that. So in order to make 9 in the first term, we're simply going to add 8 to the n. So that way, if n is 1, the denominator becomes 9. If it's 2, it becomes 10, 11, 12, and 13. And this is how you solve this problem. So we just went over a few examples that you're likely to see, the types of examples that you're likely to see in homework problems. I know this is a little different from the actual theoretical lecture, but that's why I thought it'll be useful for you to go over different examples like this. So for today, I'm going to end here. And in the next lecture, we are going to go over chapter 9.2, which is about the linear growth model. So before I wrap up, I would like to remind you to sign up for Pearson. And I guess I'll see you next time. Thank you.